These are the lecture problems for chapter 5, starting with number 8. Pause for a second and read the problem. And here we have a car that is, in this case, going to be rounding a bend. Draw the wheels on my tire, draw the person inside, there we go. Now we know that the radius of this guy, the radius of the turn is going to be 125 meters, and we know that the velocity is going to be 95 kilometers per hour. First thing we need to do is convert the velocity over to meters per second. I've left that out. You all are experts at doing that at this point, I hope. And now what we need to do is we need to draw the free body diagram on the car. It's always going to have its weight, its mass times gravity in the downwards direction, and here the road is supporting it with some normal force. Since it's rounding the bend, the force of friction between the tires and the road must be applying a force in that direction. And we also would say that this also must be static friction. Now the reason I say that is because the car is not sliding around the bend. So the first thing that we can do is we can say, okay, let me write Newton's second law. Some of the forces first in the y direction is going to be equal to the mass multiplied by the acceleration. Acceleration in the y direction is going to be 0. Now let's take a look at the forces in that direction. I'm going to have the normal force in the upwards direction. I'm going to have mass times gravity in the downwards direction. So here I'm going to have a big 0. Normal force, mass times gravity. This tells me that my normal force is equal to my mass times gravity. Now let's do the same in the x direction. Say sum of forces is going to be equal to the mass multiplied by the acceleration, and the only force in that direction is going to be the force due to friction. And I also know that the acceleration is going to be radial, so I write a little subscript r right there. And I also know that the radial acceleration is equal to velocity squared divided by the radius. So I'm going to plug that guy in right here. And I also know that my force due to friction is going to be mu sub s multiplied by the normal force. So I'm going to plug that guy in right there. I'm going to change the colors here. So here I'm going to have mass velocity squared divided by the radius. That's this term right here, is equal to mu sub s force sub normal. That's this term right here. From the y direction, I know what my normal force is. That's going to be the mass multiplied by the gravity. So mu sub s, mass multiplied by gravity. And I'm looking for the coefficient of static friction here. I'm looking for this guy. So I'm going to get that guy on one side on its own. First thing I'm going to do is cancel these masses out. They go away. And I'm going to divide both sides by gravity, just like that. And I'm left with mu sub s is equal to v squared divided by gravity and by the radius. So 26.4 quantity squared divided by 9.8, and then the radius 125. I'll point out real quick that the gravity is positive. I took the negative into account when I wrote this negative sign right there. I said it is in the downwards direction when I did that. So you plug all that in and you come up with mu sub s is equal to 0.57, and this guy doesn't have any units. Problem number 19, pause for a second and read the problem. It has a car that is rounding the top of a hill that has some radius of 88 meters. Draw my car right here. The car is traveling with some velocity of 18 meters per second. And drawing the free body diagram for the car is going to have its weight, mass times gravity, in the downwards direction, and it's also going to have the normal force, F sub n, in the upwards direction. And what it's looking for is how much is that normal force exerted by the road on the car. So what we can do is we can go ahead and write Newton's second law. Sum of forces is equal to the mass multiplied by the acceleration, and then in this case the acceleration is going to be downward, and that is also going to be a centrifugal acceleration. And what I'll actually do is, to make my life a little bit easier in terms of negative and positives, I'm going to define that to be the positive direction right there, so that makes A positive here. That means I'm going to have the normal force in the upwards direction being now negative, and then mass times gravity in the downwards direction. This is my sum of my forces, my mass times my acceleration. Acceleration is again going to be centripetal, so acceleration is going to be mass, or is going to be velocity squared divided by the radius. So over here I'm going to have mass velocity squared divided by the radius is equal to normal force and mass times gravity. I'm solving for this normal force right here, so I'm going to go ahead and I'm going to add that guy to both sides. Force subnormal, that guy is going to cancel out. I'm going to subtract off mv squared divided by r from both sides, minus mv squared divided by r. That's going to cancel out, that's going to cancel out, and at the end of the day my normal force is going to be equal to mass times gravity minus mass velocity squared divided by the radius. And I can also factor out a mass right here. I'll do that just that way I don't have to write it twice later. Gravity minus velocity squared divided by the radius. So now it's a matter of just plugging in everything that I know. I know that the mass of the car is going to be 975 kilograms. I know that gravity is going to be 9.8 meters per second squared. Velocity of the car is going to be 18 meters per second. I'm going to square that guy. And then my radius of my curve. And I go lo and behold, at the end of the day I'm going to end up with 5970 newtons is equal to my normal force of the car from the road. And you can convince yourself that this same exact setup is going to apply to the person. You know, the free body diagram is going to look exactly the same. All of this math is going to look exactly the same. The only difference for part B here is going to be that the mass is going to be different. The mass of the person is going to be 62 kilograms. This is going to be the same, 9.8 meters per second squared minus 18 squared divided by 88. So the normal force of the car on the driver is actually going to be 379 newtons for part B. And last but not least, we're looking for where the normal force is going to be equal to 0 for this for the driver. So what we're going to do is we're just going to say I want this normal force now to be equal to 0, and that's going to be, and what I'm looking for now is, you know, some velocity. So mass gravity minus v squared divided by r. I'm going to divide both sides by mass. 0 divided by anything is going to be 0. So still left with 0 here. I'm going to add v squared divided by r to both sides. So, and then I'm going to multiply, or well, I'll just go ahead and rewrite that. Write this guy. V squared divided by r is equal to gravity. Multiply both sides by r and take the square root of both sides. I end up with velocity is equal to the square root of gravity multiplied by the radius. So that velocity is going to be 9.8 multiplied by 88, square root of that guy. It's going to be 29.4 meters per second. Again, that is the speed where the normal force is equal to 0, or where you're feeling essentially weightless. Problem number 38, pause for a second and read it. It's asking if I double the mass and triple the radius of a planet, how much would g change by? And I go ahead and I take a look at maybe the lectures, or equation 5.5, both of which say that little gravity is going to be equal to g multiplied by the mass of the planet divided by the radius squared. What it's asking is what's going to happen, g prime, where I double the mass. So Newton's gravitational constant isn't going to change, but now I've doubled the mass of this guy, and I'm going to triple the radius. So I go ahead and I crank this guy out. I end up with 2 big G m, 3 squared is going to be 9.9 r squared. And I compare that expression for g with my original expression for g, and I see that g prime is going to be 2/9 multiplied by g mass of the planet divided by the radius squared. That's going to look a heck of a lot like my expression for g right here. So 2/9 of the initial gravity is going to be the gravity if you double the mass and triple the radius. So much smaller, actually, about 22% of the initial gravity. Last but not least, problem number 60. And the interesting thing is you can do this two ways. You can do it using Newton's laws or using Kepler's third law. If you follow example 512 in the textbook, what that does is that uses Newton's laws, and about the third equation down you can solve that guy for the mass of the Earth. You can also do this using Kepler's laws, in which case you simply write out the result. So what we're looking for is what is the mass of the Earth, and you know that the period of the Moon is going to be 27.4 days, and you also can look up the distance to the Moon. That's going to be 3.84 times 10 to the 8th meters. Let me just real quick convert the days into seconds. You can do that on your own. It's going to be 236.7360 seconds. And Kepler's third law is going to relate the period squared to be equal to 4 pi squared divided by big G mass in this case is going to be the Earth. That's the mass of the body that you're rotating, and then the mean distance cubed. So I'm going to make that a d to be consistent right here. I'm solving this guy for mass of the Earth, so I'm going to go ahead and I'm going to say that the mass of the Earth is equal to 4 pi squared d cubed divided by big G, and then period squared. At this point it's really just plug and chug. So 4 pi squared 2, 3, wait, we'll go put my distance in here. That's going to be 3.84 times 10 to the 8th meters. Big G is going to be 6.67 times 10 to the negative 11th, and it's got a whole bunch of units on there. And last but not least, I have my period squared, so it's going to be 2367360 quantity squared. Don't forget to cube your distance since I messed that guy up. And at the end of the day, you're going to calculate 5.98 times 10 to the 24th kilogram. You check that with your book, and you see that you came up with a value that makes sense.